When analyzing algorithms, one of the key goals is to evaluate their efficiency in terms of time and space. However, it can be challenging to express the performance of an algorithm precisely, especially as the input size grows. This is where asymptotic notation comes in. It provides a mathematical framework to describe the behavior of an algorithm in a specified yet meaningful way. Hello, all. Welcome back to Being Passionate Learner. I hope you all are doing great. This video is third lecture on design and analysis of algorithms. Today we will discuss asymptotic notation and analysis. But before we get started, if you are new here or haven't subscribed yet, hit that subscribe button and turn on the bell notification so you never miss any of my upcoming videos. I have planned the amazing contents for you. Now, let's get started. In this video, we will explore the purpose of asymptotic notation, how it helps in simplifying complex expressions, why we ignore constant factors and lower order terms, big O notation, big omega notation, big theta notation, and practical examples of asymptotic analysis. So let's get started with the purpose of asymptotic notation. Asymptotic notation helps us focus on the growth of an algorithm rather than its exact runtime or memory uses. The goal is to describe the efficiency of an algorithm in a way that is independent of hardware, programming language, or implementation details. Provides a clear understanding of how an algorithm performs as the input size n increases. Compare algorithms based on their scalability and performance for large inputs. By using asymptotic notation, we can generalize performance analysis, making it easier to choose the best algorithm for a given problem. Simplifying complex expressions. In real-world scenario, the runtime of an algorithm can be expressed as a complex mathematical formula. For example, suppose the runtime of an algorithm is given by T of n is equals to 5n cube plus 3n square plus 8n plus 20. This expression has multiple terms, making it hard to analyze at a glance. However, asymptotic notation allows us to simplify it by focusing only on the most significant term that dominates the growth rate of n. In this case, 5n cube is the dominant term because it grows the fastest as n increases. We can simplify t of n to big O of n cube, which makes the expression much easier to work with. Another key aspect of asymptotic notation is ignoring constant factors and lower order terms. Why ignore constants? Constants depend on specific implementation details such as the speed of processor and how efficiently a particular operation is executed. However, these constants do not impact the overall growth rate of the algorithm. For example, 2n and 100n are both considered big O of n because their growth rate is linear and the constant multiplier becomes irrelevant for large inputs. Why ignore lower order terms? As the input size increases, lower order terms have a negligible impact on the overall runtime. For instance, in T of n is equals to n square plus n, the n square term grows faster than the n term for larger values of n. Thus, the lower order term n can be ignored and we can approximate T of n as big O of n square. By focusing only on the dominant term, the ignoring constants and lower order terms, asymptotic notations provide a clear and practical abstraction of algorithms' performance. By using asymptotic notation, we can compare algorithms in a meaningful way and make better decisions when designing efficient solutions. Big O notation. In the world of algorithm analysis, Big O notation is a crucial concept that helps us understand how an algorithm will behave as the input size grows. It specifically provides the upper bound of an algorithm's growth rate representing the worst case scenario in terms of time or space complexity. Let's dive deeper into what this means with an example and understand why this upper bound is so important for evaluating an algorithm's efficiency. Big O notation describes the upper bound of an algorithm's performance, which tells us how the runtime or the space requirements of an algorithm will grow as the input size increases. Upper bound means the Big O provides a guarantee that the algorithm will never perform worse than the specified growth rate, even in the worst case scenario. It ensures that no matter of the size of input, the algorithm's performance will not exceed a certain threshold. Worst case scenario refers to the slowest possible execution time or the highest space uses. This is especially important in situations where predictability and reliability are required, such as in real time systems or large scale applications. Big O notation essentially sets the maximum limits of a growth for an algorithm, making it an essential tool for understanding how an algorithm will scale. Let's consider the following function representing the time complexity of an algorithm. F of n is equals to 3n square plus 2n plus 1. This function has three terms. 3n square, which is quadratic term, which grows faster as n increases. 2n is the linear term, which grows at a slower rate than the n square. 1 is the constant term, which remains the same regardless of the size of an n. As n grows larger, the 3n square term will dominate the function and the 2n and 1 terms will become less significant. For very large values of n, the runtime of the algorithm will be approximately proportional to n square, even though there are smaller terms in the equation. In Big O notation, we focus on the dominant term, so we can express this function as Big O of n square. This means that the algorithm's time complexity grows quadratically with the input size, and we can ignore the smaller terms and the constant factors for large n. The significance of Big O of n notation lies in its ability to ensure maximum limits of growth. When we use Big O, we know the worst case growth rate of an algorithm. It allows us to predict performance. Big O gives us a clear understanding of how an algorithm will scale with larger inputs. If an algorithm has a time complexity of Big O of n square, we know that its runtime will grow quadratically as the input size increases. Big O makes informed decisions. With Big O, we can compare algorithms and select the one that performs better in terms of scalability, particularly for large scale data or real time systems. For example, if we are choosing between a quadratic algorithm and a linear algorithm, we would likely choose the linear one for larger datasets because it grows more slowly. Big O avoids inefficiencies. By analyzing the Big O of an algorithm, we can spot potential performance bottlenecks and make improvements before scaling up the problem. The formal definition of Big O states the function f of n is equals to Big O of g of n if and only if there exists positive constant c and n0 such that f of n is less than or equal to c into g of n for all n is greater than n0. This means that f of n will never grow faster than g of n multiplied by some constant c starting from a certain point n0 onwards. For sufficiently large n, the growth of f of n will always be less than or equal to constant multiple of g of n. N0 is a threshold beyond which this relationship holds. The constant c allows for some scaling factor, ensuring that f of n remains bounded by g of n as the input size grows. Big omega notation. When analyzing algorithm, we often want to understand not just the worst case performance Big O, but also the best case scenario. This is where the big omega notation comes into play. Big omega provides the lower bound of an algorithm's growth rate, representing the minimum time or space required in the best possible case. Consider the function f of n is equals to 3n square plus 2n plus 1. In this case, as n grows larger, 3n square term dominates the function. Therefore, the lower bound of this function describing the best case scenario is omega of n square. Big omega is especially useful when we need to set performance guarantees for an algorithm. By knowing the lower bound, we can confidently state the minimum time or the space algorithm will require regardless of its input variations. We say that f of n is equals to big omega of g of n if and only if there exists positive constant c and n0 such that f of n is greater than or equal to c into g of n for all n greater than n0. This means that big omega represents the best case minimum performance of the algorithm. It tells us that no matter the input, the algorithm will not perform any better than a certain threshold, even in the most favorable conditions. Now let's discuss Big Theta notation. When analyzing the growth of algorithms, it's often helpful to have a precise understanding of how their time or space complexity behave. While big O and big omega gives us the upper and lower bounds, big theta provides a more accurate and tight bound. This notation tells us how an algorithm grows in both the best case and the worst case scenarios, providing a more balanced view. Let's look at the example f of n is equals to 3n square plus 2n plus 1. For large n, the quadratic term 3n square will dominate the growth of a function. Therefore, we can express the growth of the function using big theta notation as big theta of n square. Big theta notation is particularly useful because it provides a more precise and more accurate representation of an algorithm's average case growth rate. Unlike big O, which only gives the upper bound, or big omega, which gives the lower bound, big theta captures the algorithm's growth from both ends, ensuring that we have a complete understanding of its performance. Big theta notation gives us a tight bound on the growth of a function. Especially, we say that f of n is equals to big theta of g of n if and only if there exist positive constants c1 and c2 and n0 such that for all n greater than n0, c1 into g of n is less than or equal to f of n is less than or equal to c2 into g of n. This means that f of n and g of n grows at the same rate for large n within the constant factors. Big theta provides both the upper and lower bounds for the function, meaning that it tightly bounds the growth from both ends. Essentially, big theta gives us a precise average case growth rate of the algorithm as it tells us that the function f of n behaves asymptotically like g of n. Let's now discuss practical examples of asymptotic analysis. Asymptotic analysis helps us choose the most efficient algorithms for real world problems. By understanding time complexities, we can predict performance for different input sizes, leading to more optimized solutions in applications like searching, sorting, and matrix operation. Let's discuss this one by one. Searching algorithms, linear search, big O of n. Linear search searches each element one by one. Its time complexity grows linearly with the input size. Binary search, which is big O of log of n. Binary search efficiently narrows down the search space by half each time, making it much faster than the linear search for large datasets. Sorting algorithms, merge sort, big O of n log n. It is efficient for large datasets. It performs well in most cases. Bubble sort, big O of n square. Bubble sort performs poorly with large data sets due to its quadratic time complexity. Matrix multiplication. Naive matrix multiplication. Naive matrix multiplication is traditional approach where three nested loops result in a cubic complexity. Strasson's algorithm. Strasson's algorithm is optimized algorithm that reduces the complexity and making large matrix multiplications more efficient. To wrap it up, asymptotic notation is a powerful tool for analyzing algorithms. It helps us to make informed decisions on which algorithm to use for optimal performance. If you found this video helpful, don't forget to like, subscribe, and hit the bell for more algorithm insights. Thank you for watching. I will see you in next one. Till then, being passionate learner, keep learning.